All right, so what I want to do in this video is essentially do some applications of the Lebesgue-Dominique convergence theorem. I'm actually largely going to do section 4.5, which the whole section is essentially one big application of the monotone convergence theorem. So first, I want to prove a fact about Fourier transforms as a very typical example of how to use the Lebesgue-Dominique convergence theorem. So before I do that, I want to actually go over Euler's formula. I'm not sure if everyone has seen it. But anyway, so if z is a complex number, z equals x plus iy, then I'm going to define e to the z to be this infinite series. Okay? You will prove in 513a that this converges absolutely, and it converges uniformly, in fact, on bounded subsets of the complex plane. It's very, very easy to prove all those facts. Just would take us too long to do it. But anyway, so one thing you should notice is that, well, first of all, I should mention this is a reasonable definition for e to the z. Just defining it as a power series. There's no really ambiguity here. I mean, convergence, there is ambiguity, but it really does converge. So in particular, let's look at what happens if we just plug in ix for some real number x. Okay, so just dump, instead of z, we have ix, so this is the definition. Okay, now let's do a little trick here of sorts. Let's break the sum up into the even terms, k equals 0, 2, 0, 2, 4, 6, etc. And the even terms, k equals 1, 3, 5, 7, etc., etc. Okay. So I haven't really done anything yet. So let's see what's going on here. Well, let's look at the even terms here. I squared is -1, okay? And that means I to the fourth is -1 times -1 is 1. That means I to the sixth is I to the fourth times I squared, which is 1 times I squared, which is -1. So we get 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial, etc., etc. Okay, and you should know what that is. On the other hand, let's factor out an I here. So this would give us just x. This would give us I squared x cubed, I to the fourth, x to the fifth, over 3 factorial, 5 factorial, 1 factorial. Okay. And let's see what that is. Well, first of all, you should remember that this is cosine x. Okay, and I squared is -1, I to the fourth is +1, I to the sixth. Again, we just had it before, it's -1. So this here would be x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, etc., etc. And you should recognize what this power series is. It's none other than the Maclaurin series for sine. So that means e to the ix is cosine x plus I sine x. So you'll notice that the absolute value, the modulus of e to the ix, is just 1. Just add modulus of cosine x plus I sine x. Well, it's just square the real part, square the imaginary part, add them, take the square root. Cosine squared plus sine squared is 1. Square root of 1 is 1. Okay, so an application of this and the Lebesgue-Dominique convergence theorem is to Fourier transforms, which maybe you've seen, you've taken AMAT 311 differential equations or analysis for applications. I forget the 314, 315, AMAT 314, 315. So let's say f is an integrable function on the real line, so it's Lebesgue measurable, and the integral of the absolute value is not infinite. Let's define the Fourier transform in the following way. Just integrate over r e to the ixy f of y dy. You often have a 1 over 2 pi I to make the inverse Fourier transform very nice and to make it almost the same as the regular Fourier transform. That's not something I really want to get into. Though I should actually mention an easy way to prove what's called Plancherel's theorem, the theorem on inverse Fourier transforms, is to use the dominant convergence theorem. But if we had time, we absolutely would talk about inverse Fourier transforms and prove results about that. But anyway, so we're just content here to prove this tiny little theorem that the Fourier transform is continuous. All right. This is not a comma, it's just a pencil mark that didn't get erased. Okay, so how do we do this? Well, we're going to use the sequential criteria for continuity, or however you called it. We're going to use the equivalence of continuity involving sequences that converge to some x0. So we're going to prove f hat is continuous at x0 by looking at a sequence converging to x0. Okay. And what we're going to do is we're going to prove that f hat of xn converges to f hat of x0. So how do we do that, and what on earth does this have to do with Lebesgue dominant convergence theorem, or let alone sequences of functions? Well, we're going to associate naturally a sequence of functions to this problem. And it's fairly obvious how you would do it. Let's say fn tilde of y is e to the I xn y f of y. Okay. So the point here is that you'll notice that f hat of xn is just the integral of fn tilde of y dy. Okay. So first of all, let's just notice something fairly trivial, and that is fn tilde of y converges to e to the I x0 y f of y. E to the I xn y, in general, e to the I x is continuous because cosine is continuous and sine is continuous. So just from that fact, we have trivially that e to the I x and y times f of y converges to e to the I x0 y f of y. F of y is just f of y; it just sits there, it doesn't do anything, and it's a complex number. And same thing with y. Y is just y; it just sits there. So clearly, x and y converges to x0 y, and therefore e to the I x and y converges to e to the I x0 y, and therefore this whole thing converges to this whole thing here. So let's define this as f tilde of y. So I guess I could have put double dots here because I'm really defining fn of tilde of y to be this here. So yeah, let me do that. Anyway, okay. So you'll also notice, and this, this happens quite often, and this is what makes the dominated convergence theorem so useful, Lebesgue dominated convergence theorem. Usually when people say the dominated convergence theorem, they mean the Lebesgue dominated convergence theorem. There is just one dominated convergence theorem. Anyway, So this here is the absolute value of e to the I x and y times the absolute value of f of y. And we know the absolute value of e to the I x and y is 1. So this is literally equal to the absolute value of f of y. And we know f of y is integrable. So we have an integrable dominator for all these fn's. And sorry, this should be, wait 1 second. This should be right here, f, yeah. Should be fny tilde. So. Okay, so, right, so we're almost done. Okay, so by Lebesgue-Donnelly convergence theorem, let's define big F of x 0 to be the Fourier transform of. So actually, yeah, we can make this. Let's make this f hat instead. So this is f hat, and make this f hat. Okay, so yeah, f hat of x0 is exactly this integral. That's how we define the Fourier transform f hat. Okay. Which is, again, the integral of this function here. But fn tilde converges to f tilde on R. And it's dominated by absolute value of f of y for every y and every n. And this is integrable, so by the Lebesgue-Donnelly convergence theorem, these two are going to be equal. And again, we integrate fn tilde of y. That is literally this integral here. Again, this is this right here. What I have right here is fn tilde of y. Okay. And I mean, just, and again, right here, this is f tilde. Sorry, it's a little awkward to write on my digital pad, but okay. Right, and like I said, integrating fn tilde of y is this, which is just the Fourier transform of f hat of xn. So we've carefully proven that f hat of x0 is the limit of, as n goes to infinity, of f hat of xn if xn converges to x0. And that proves continuity. Okay. So yeah, I'll leave it for homework that if we assume, actually, I don't think we need to assume any more to get that this is actually differentiable on the real line. But I'll leave that as a homework that I will assign. And it's basically the same idea, except you would have to be a little more clever in getting a dominator, and you have to use a mean value theorem, but anyway. Okay, so another application, and this is very similar to what we did using the monotone convergence theorem, so I'll go quickly with this, and that is proving countable additivity for integrating integrable functions. So let f be integrable on E, and let's say E is a disjoint union of these EKs, everything is measurable. Then the integral of E, integral over E of f of x, is just the sum of the integrals. And a proof, yeah, it's just like, actually, I don't remember if we proved this for, I don't think we did prove it for non-negative functions. I have to go back and see. But anyway, so, right. So let's say Fn is this, again, we're going to associate naturally a sequence of functions to this problem. And the natural thing to do is to just take the sum of f of x times characteristic function of ek of x. So if x is an e, then clearly there exists an n where x is an en. So we know then what Fn of x is. These are all disjoint. So if k is not big N, then this characteristic function is 0. Okay. And therefore, this is just 0. We're assuming f is complex valued, so we're not worrying about 0 times infinity. And again, I mentioned in the last video that that if a function is integrable, then it's finite almost everywhere. So you can excise a set of measure 0 and assume that f is just complex valued everywhere without changing the value of the integral. Okay. So, right. So, yeah. If k is not big N, then characteristic function of ek is 0. So in particular, if little n is less than big N, then none of these are e big N, because k is between 1 and little n is less than big N. So all of these characteristic functions are 0. So this is 0. And on the other hand, if little n is bigger or equal to big N, then, well, when k is big N, and it will be big N eventually, because little n is assumed to be bigger or equal to big N here, then this is just going to be 1 for k equal to big N. So this is just f of x. So that clearly means that, well, like before, this is a dominator for the sequence of functions, absolute value of f of x. And point-wise, we have convergence on E. That's pretty trivial. Fn of x is f of x for large enough n, depending on x. We're not claiming uniform convergence. It's not going to be uniformly convergent in general. Big N absolutely depends on x. And this says x is an En. It looks like an E, but it's is n. Okay, so we can just use the dominated convergence theorem and then just read off what this limit is. And not that it matters, but there should be a dx here. Just annoys me. So. Okay, just dump in for what Fn of x is, nothing more than that. Okay, and we proved that at least for two functions, the integral of a sum of two functions is a sum of the integrals, but by induction that applies to any finite number of functions. So we can interchange this integral and this finite sum. And we know, at least homework, is that when you integrate f of x times a characteristic function, it's just the same thing as integrating over ek. And we know by definition that the limit as k equals 1 to, the limit as n goes to infinity of the sum k equals 1 to n is by definition this infinite sum. So one subtle point here, and this is really encoded, this is the power of the dominated convergence theorem. The dominated convergence theorem, remember, not only proves that you can interchange the limit and integral, but in particular that it proves that this limit even exists. which is the same thing in this context as proving that this infinite sum even exists. So this is saying not only does this infinite sum of complex numbers exist, it's going to be equal to this integral here. Okay, and this last result is not really an application of the Dynamic convergence theorem, it's an application of what we just proved. And that's continuity of, well, it's really continuity of integration. I'm calling it continuity of measure. But anyway. So it's basically continuity of measure for integration. Or in other words, f integrating against a function behaves like Lebesgue measure, which, as I mentioned, is extremely important for probability theory. If you ever want to, get your hands on and prove things, deep in probability theory, you need to know that integrating against the probability distribution function is satisfies the same extremely useful technical properties as Lebesgue measure. So in particular, you would have something like Borel-Cantelli. And you can Google Borel-Cantelli, and they'll have a probabilistic version of it on Wikipedia. And there's a humorous application of it, which is, in theory, if you have, I hope I get this right. In theory, if you have monkeys, if you have a monkey just hitting random keys on a keyboard, then this eventually, with probability 100%, eventually the monkey will hit all the letters in a Shakespearean book. It's on the Wikipedia page on Borel-Cantelli. But anyway, I thought that's kind of funny when I saw it. All right, so let's say f is integrable on E, and we have a collection of measurable subsets of E. One, if this is ascending, then the integral of the union is the limit of these integrals. And if the EKs are descending, then the integral of the intersection is the limit of the integral. So I'll just make this a little brighter. Not that it matters because this is for homework, but at least part 2. Actually, you should recall that we used continuity of measure to prove Borel-Cantelli. So, right. Okay. Yeah, maybe I'll actually assign like a probability like homework proving Borel-Cantelli for functions, but anyway. Okay, so the proof is just like continuity of measure. That's the whole point. The whole point is that, this should fall from the countable additivity of integration, just like it did for Lebesgue measure, just like the continuity of measure just immediately fell from this was immediately proved by the countable additivity of Lebesgue measure. All right, so we do that disjointification process, the second part of it. Just remember, because these are ascending, we can define E1 prime to be E1 and EK prime to be EK, take away EK minus 1 for K bigger or equal to 1. And if we do that, we get this unions are the same, except that these are disjoint. And here's the obvious picture. Again, this old stuff. So it's kind of like the, it's like take an onion and we're kind of breaking the onion up into its layers. This is like the core. E1 prime is E1. E2 would be this whole thing here. E2 is just the stuff between E1 prime and E2. E3 is this whole thing here. E3 is just the stuff between, E3 prime is the stuff between E2 and E3. Again, in case I didn't say this right, E2 is this whole thing here. E2 prime is the stuff between E2 and E1, and et cetera, et cetera. Okay, so, right, and this is, everything's measurable here. So, yeah, so we can just use countable additivity right here. And then, like before, what's the definition of this infinite sum? It's just the limit of the sum as k equals 1 to n. Okay. Now, E1 prime is E1. Okay. E2 prime is E2 take away E1. So this is shorthand for integral of f of x dx on E2 minus integral of f of x dx on E1. And this would correspond to k equals 3. This exactly is the integral of E3 prime f of x dx, et cetera, et cetera. And just like with continuity of measure, you'll notice, let me get this stupid thing out of the way. Right, so you'll notice that, well, the E1s cancel. So let me do it like this. I'll just cancel the integral sign. Yeah. To denote that the integrals cancel out. Okay. The E2s cancel out. If I wrote the next term, you'll see the E3s would cancel out. And go all the way back, if I wrote the term before, the En minus 2 terms would cancel out. The En minus 1's term cancel out. Well, the ENs don't cancel out. You're ending here. So this is the only thing that survives this ordeal. And so you're left with this limit of integral En f of x dx. So yeah, that proves it. Yeah, and again, I think I'll put for homework a very easy homework, because it's just literally look in the book for Borel-Cantelli, the proof. But I'll put as a homework like a probability version of Borel-Cantelli, which you don't need to know any probability. It's literally just integration. Okay. So next up is going to be another very, very, very important probability topic, which is going to be convergence in measure. We actually already seen a little bit of convergence in measure on the exam. So I'll save us a little bit of time, because that's one of the major results, is that pointwise convergence implies convergence in measure, which was literally exam problem 5, which happily everyone basically got. So happy about that. Yeah, and the exams were pretty good. So, all right. Yeah, so you'll get a new video maybe in a couple days. And we'll probably, so it went definitely slower than I expected and hoped, but I hope no one's going to complain that I've been going at a snail's pace, putting in a ton of detail. I usually don't, when I teach this course in general, I don't put this much detail, but so we're going to finish off next week with normed vector spaces and LP spaces, which is a good place to leave off, and it's a very useful way of thinking about integration and functions, talking about vector spaces of functions and norms on these vector spaces. And you'll take a little peek into the beautiful area of functional analysis, which is combining linear algebra and real analysis. And if this little window is going to really appeal to you, we often, we might actually be doing it next semester, I don't remember, but we often have a functional analysis course being taught that you're more than prepared for if you've taken this course. Okay, so long, take care. And again, let's take inspiration from this little guy here. So be jolly, be happy, and you know, yeah. All right. See you later. See you soon.